Hello, everyone. The following is the fourth in a series of videos covering chapter 36. Today, we're going to be talking about images formed by thin lenses. So, last section, we talked about the refracting surface. Basically, had light refracting from one medium to another. Now, what if you have light refracting into a medium and then refracting back out into the original medium, like with a prism? That's essentially what we see when light goes through a lens. And lenses are employed by anyone wearing glasses, cameras, telescopes, and microscopes to basically take advantage of refraction to form images of different sizes. Now, a lens then is a kind of like a two-sided refracting surface, right? You can think of light passing through a lens by something like the drawing shown the lower right, where light kind of refracts into the lens and then within the lens refracts again coming out of it. Kind of like like we saw with the prism. So there's twice the amount of geometry to account for compared to the refracting surface of the last section. Now you have the radius for the front part of the lens and the radius for the other side of the lens. And there is a sort of equation that, again, it's all about letting you find the location of the refracted image once light passes through both sides of the lens. So this equation here is shown below. As long as you know n, which is the index of refraction of the lens, and the curvature of both sides of the lens, then you're able to find the location of the image. And as you can see in the drawing here, right, the image overall ends up on the other side after being refracted twice. So the lenses do have a focal point, which is defined the same way as mirrors. If the object is infinitely far away, so you have these parallel incident light rays, the focal point is where the parallel rays converge. The drawing A shows a converging lens, and you see how parallel light rays converge in front of the lens, across the lens on the other side of the lens, while the drawing number B shows a diverging lens where the rays appear to converge on the opposite side of the lens. So whichever way the light rays go, whether they're moving to the left or to the right across the lens, they will pass through or appear to pass through one focal point or another. Each lens has two focal points. Each one is the same focal length away. So to find the focal length, you can take the formula we talked about for finding the image distance, and much like with concave mirrors, right, there's a point where the object can be moved so that it's essentially infinitely far away, right? That's why you get those parallel rays approaching the lenses. So when that happens, since we know that light rays then will converge at the focal point, we can take the formula and make the object distance infinitely big. And what that leaves us is that the image distance will be the focal length. So we get the lens maker equation from that, which tells us that the focal length depends on the index of refraction of the lens and the radius of both sides. So once you have the formula, then you can kind of craft your own lenses with their own curvature and index of refraction to obtain a desired focal length. Following that, once you know the focal length of the lens, and with the assumption that the lens is thin, which is just saying that the thickness of the lens is much smaller than the curvature of either side. And unless told otherwise, we're going to assume that the lenses we work with in examples are all thin, so that we can apply this thin lens equation that easily lets us find the location of the refracted image across or appearing to show up behind the lens, depending on where the object is or what kind of lens you're dealing with. So this is the same formula for mirrors. The sign convention, though, is a bit different for mirrors, so we'll talk about that here. Whatever the front side is considered to be where the object is sitting at, so that's where incident light emerges from. Where the object sits, its distance to the lens is measured as positive. If the image converges across the lens, it's a real image, so the rays will diffract towards the central axis and physically converge, creating a real image, which also makes the item distance, the image distance, positive. If the image is virtual, so the image appears to be from the front of the lens, so the same side as the object, then that is in fact a virtual image, and Q will be measured as negative. So that's when, right, the light rays don't actually converge, they just appear to. So that's why the front side is considered the virtual side, and the back side is considered the real side. Now, the focal length will be positive for converging lens because the parallel rays do actually converge, while the diverging lens, the parallel rays only appear to diverge, so focal length is negative. Kind of like a convex mirror. So converging lenses have a convex shape, while converging mirrors have a concave shape. Diverging lenses have a concave shape, while diverging mirrors have a convex shape. So here you can see a few different shaped lenses that exist. If you wear glasses, you're probably wearing some kind of like convex concave mixture. And of course, when images are sent through the lens, they get magnified, and with some, again, similar arguments to geometry, it turns out that the magnification of the image can be found with the ratio of the image distance to the object distance. And the sign convention is the same, right? For a positive magnification, tells you that the image is bright and it's in the same side of the lens of the object. That means it's virtual. The rays appear to emerge from the side of the object, even though they're not actually converging anywhere. If M is negative, the image is inverted and it's opposite of the object, so the refracted rays are actually converging and you have a real image. So you can do ray diagrams like with mirrors to figure out where the image is going to be. You should have to have a good scale to properly draw where the object's located and where the focal point is. The rule is always to draw 3 rays. The first one is going to be parallel to the principal axis, then refracts through the focal point on the other side. The second one will pass through the focal point on the front side and refract parallel to the central axis. The third point goes right through the center of the lens without refraction, since the way that it hits the normal on both sides makes it have no change in angle. Now, there is a situation though where the object is in front of the focal point on the front side of the lens, so ray number 2 can't pass that focal point since you're ahead of it. In that case, you draw it as if it were coming from that focal point, even though it's not. So you can see on drawing B what I'm talking about with the green ray, where it's an object in front of F1, so the green ray starts ahead of it, but you can see how you can trace it back to the focal point. Also, it's worth pointing out that for converging lenses, much like the convex mirror, so for converging mirrors and lenses, when the object is outside when the object is far from the mirror and the focal point it'll create an inverted real image on the backside of the lens. When the object is between the focal point and the lens, it'll create an upright virtual image behind the object, and it'll be magnified. It'll be bigger than the actual object. Diverging lenses, much like diverging mirrors, can only create virtual images, those that appear on the same side as the object. The ray diagrams, again, follow the same idea that the first ray starts off parallel to the axis, then appears to come from the first focal point. The second ray appears to move towards the focal point across the lens, and then refracts parallel to the axis, and then the third ray goes straight through the middle. So wherever those three rays appear to intersect, that's where the image will be formed. And for this type of lens, again, the image is virtual, it's going to be upright, and it's always going to be minified, and it'll appear on the front side of the lens. So here's a summary then of the different ray diagrams you can end up with. So there's two cases for the converging mirror and one case for the divergent one. Also, we're assuming, right, that the rays here are making small angles with the axis, and that the curvature of the mirror is much bigger than the distance between the principal axis and the rays. So basically, we're saying that the lens itself is much bigger than the light rays coming off the axis. Which, again, unless otherwise stated, we'll assume that the lenses and mirrors we deal with can all be shown through ray diagrams. So what is the focal length of a pane of window glass? This is equivalent of a bathroom mirror. A pane of window glass being flat has a basically infinite range of curvature. So if you recall the focal length formula, it was right here, the Lens-Merkers equation. If the radius is infinitely big, then what that means for the focal length is that the focal length is infinitely far away. It's the same thing. Again, it's equivalent of a bathroom mirror. Flat mirrors have a focal point infinitely far away, right? Because think about a pane of glass. Think about how we define the focal point, the focal length. If you shoot a bunch of parallel rays towards a glass, a flat glass, they'll just pass right through. They will not refract. So they won't converge ever. And that's, mathematically speaking, that's the same as having a focal length of infinity. They never reach a conversion point. So what if you have two lenses or three lenses in a row? What happens then? Well, to figure out what the final image will look like after it passes through all the lenses, you can take this one step at a time. So first consider the image formed by the first lens. That image is now going to become the object that lens 2 is refracting. So you can then do a lens equation for the first lens to get the image location. That's going to become the object location for lens 2. And from that, you can get the image location. That'll tell you where the image is formed across lens 2. Now, you got to be careful though with the signs, right? Because what could be a negative sign distance with respect to lens 1 could be positive with respect to lens 2. If an image or an object is between lens 1 and lens 2, then the distance will be negative for lens 1 and positive for lens 2. Or you can also solve the problem with the same point of reference. So from wherever the object stands, you can refer to all your distances with respect to there. But again, it's just being careful with the sign convention. Also, every time that you send light through a lens or a mirror, the resulting image gets magnified. So the image that gets created passing lens 1, which then lens 2 refracts, is magnified, which means that the total amount of magnification is the product of the magnifications of all lenses and mirrors present in your combination. In this case, there's only two lenses, so total magnification is a product of the two. Now, what if you have two lenses basically glued together? Again, the assumption is that they're really thin. So you can work out the two separate lens equations, but essentially it simplifies to the formula shown here at the top, which is similar to the lens equation, but now you have an extra term for the second lens's focal length. And P is the object distance right in front of the pair of lenses, and Q is the final image once light has passed through both lenses, once it has refracted through all of them. So you can actually find an equivalent lens that represents this too, kind of like an equivalent resistor in circuits. You can find an equivalent lens with a focal length that's related to the individual focal lengths for the formula shown at the bottom. In other words, two thin lenses that are next to each other is equivalent to a single thin lens whose focal length is shown in the equation. That means that the combined focal length of two lenses is smaller than their individual focal lengths. And that's it for this section. Hope you join me next time.